Okay, so I'm going to discuss a bit more about phase structures that you can get out of tropical polyhedra. The motivation here is that a lot of algorithms depend on interplay of faces of ordinary polyhedra, and if we want to tropicalize these algorithms, then we would like similarly nice phase structures for tropical polyhedra. So what I'll end up talking about is how we can define these phase structures, and then a bit about the issues with them. And then if I get a chance, I will start talking about how we can start to mitigate these issues and make tropical phases the best that we can make them. Providing I get to some of our results, this is joint work with Gil Gloho, who's University of Twente, and we'll be speaking in an hour's time. Okay, so I will be just going over some of this. I might go over some of the stuff that Stefan's already talked about, but to see it twice doesn't hurt. So I'm working in the max plus semi-ring, where we have minus infinity, and addition is max, and multiplication is addition. And then a tropical half space, HA, is a subset of tropical D space that satisfies some tropical affine inequality. So some inequality that looks like this. What do these sets look like geometrically? Well, we can look at a tropical hyperplane. So this picture down here is a tropical hyperplane. It is a fan, and it's a fan that splits D-dimensional space into D+1 sectors. And these sectors correspond to which term of a tropical linear inequality has been maximized. So if the second term has been maximized, then we are in sector 2. A tropical half space is some coarsening of this tropical hyperplane. So for example, in this max plus inequality down here, what I have is because I have a -2 and a -4 attached to x1 and x2, my hyperplane is at apex 2, 4. And then how I coarsen this hyperplane, all those on the left side of all the terms on the left side of the inequality are those maximized, so those are those contained in the half space, and those are not contained in the half space. So this gives me my tropical half space. And then my slides freeze, there we go. And a tropical polyhedron is just an intersection of finitely many tropical half spaces. So here I have 3 tropical inequalities, affine inequalities that give 3 tropical half spaces, and their intersection is this tropical polyhedron given in gray, and it's unbounded. So from a linear programming point of view, this is the most natural definition of a tropical polyhedron, just the intersection of tropical half spaces. But there are other ways we can define tropical polyhedra. We don't have to just use this external description. We can use an internal description by defining it in terms of vertices and rays. So this is a theorem of Stefan and Ricardo Katz, the tropical analog of the Minkowski-Weil theorem, which states that we can write any tropical polyhedron as the tropical Minkowski sum of a tropical polytope and a tropical cone. So Stefan's already defined a tropical cone very helpfully for me, but I'll just go over it once more. A tropical cone is given by some generators W, is just the tropical conic combination of those W's, whose coefficients are anything in the max plus semi-ring. An example of a tropical cone is this picture down here. A tropical polytope is very similar, except now we're taking the tropical convex hull, and so we need a condition that the sum of the coefficients in this convex combination all sum up to tropical 1. So they all have to, the maximum they can be is 0. And so this gives a tropical polytope like so. This is just the tropical convex hull of these 2 points, 0, 4 and 2, 0. It's a line segment, or a tropical line segment. And so the tropical Minkowski-Weil theorem states we can write any tropical polyhedron as the tropical Minkowski sum of a polytope and a cone. And so here I've written this previous tropical polyhedron as the sum of a polytope and a cone. And this means we can actually define vertices and rays for this polyhedron. The generators for the polytope, there is a unique minimal generating set of generators for this polytope. And so these are the vertices of my polyhedron. And there is a unique minimal generating set of ray generators for this cone up to addition of scalars. And so these will be the rays of my polyhedron. So this gives an internal description for my tropical polyhedron. And then there's a third way we can sort of view these. Rather than just thinking these as purely max plus objects, we can think of them as the image of ordinary polyhedra or Puiseux polyhedra in some valuation map. So again, Stefan has nicely defined this for me already, but I will just quickly reiterate. I'm going to look at the field of real Puiseux series. These are formal power series of this form. The coefficients and the exponents are allowed to be real numbers, but and I'm allowed infinitely many terms, but there has to be some well-defined maximum A0 being the maximal exponent, and then we're strictly decreasing from there. There is also some other technical conditions on they have to, if you take any sort of finite amount of these, they have to be, you can't, they have to be well ordered. There's some other technical well ordering conditions to make sure this is really a field and everything plays nicely. So we can start doing convexity in this field by defining by saying that a formal power series is positive if its leading coefficient is positive. And given this, we can order Puiseux series. And so a real Puiseux series, say A is greater than B, if and only if A minus B is positive. So this gives an ordering, a total ordering on the real Puiseux series. And what this means is we can now formulate, we can do convexity over, and we can formulate polyhedra over real Puiseux series. A priori, there's no guarantee that these polyhedra may behave well, but it turns out that they do because real Puiseux series are real closed, which on a technical level means any first order statement over the Puiseux series is the same as over the reals, but on a less technical level means polyhedra behave pretty much exactly the same over R as they do in real Puiseux series. In particular, what we can also do is we can think of this T as a variable that we can substitute another real number into, and so we can genuinely get some real polyhedra out just by this substitution. So we can formulate polyhedra over this field perfectly fine. How does this connect to tropical polyhedra? Well, this is a valued field, and it comes with a valuation. And the valuation is given as follows. To any Puiseux series, we take the leading exponent, the largest exponent of this Puiseux series. This is going to be some real number, or in the case that our Puiseux series is 0, then we define this set this to be minus infinity. So if you haven't seen this before, here's some quick examples of how this valuation map acts. Obviously, the valuation of t squared is just going to be 2. The valuation of this slightly larger expression here, we just take the leading exponent, or this is 3 from t cubed. And then finally, just to show that we don't need these expressions to be finite, here I have some infinite series, but there is some well-defined leading term, and that is t to the 0. So the valuation of this is just 0. So this is how this valuation map acts. And so what we can do is we can look at polyhedra over the Puiseux series and then take their valuation, and we end up with tropical polyhedra. So as an example, here I have some, ignore the dotted one for the moment. I have some Puiseux triangle. It's just the convex hull of these 3 points in the Puiseux plane, I guess. And what we can do is we can take the pointwise valuation of this triangle and we get the following tropical triangle. It looks slightly odd in that we have like a 2-dimensional bit and then these 1-dimensional tentacles hanging off, but that is all perfectly fine. This is what we expect tropical polyhedra to look like. But the one crucial thing here is that this is not the only Puiseux polyhedron that maps to this tropical polyhedron. What I can do is I can, because the valuation map only remembers the leading exponent of any of these entries, I can add lower degree terms, I can change the coefficients, and under the valuation map, I'm going to get mapped down to the same tropical polyhedron. So this dotted triangle over here is a slightly more convoluted triangle, but it's still just a triangle and it gets mapped down to this tropical triangle. So this seems perfectly fine at the moment, but things can get a slightly stranger when we go into a slightly more convoluted high dimensional examples. So this is an example from a paper by Devlin and Yu. And this is a 3-dimensional tropical polytope. We have this 3-dimensional stack of cubes here, and then these 2-dimensional flaps that sit on the outside. And there are lots of different tropical Puiseux polyhedra that map down to this, this tropical polytope. But crucially, whereas in this previous example, we just got triangles that map down to this triangle, here we have different combinatorial types that can map down to the same tropical polyhedron. So for example, if I look at this Puiseux polyhedron here, I have a face ACD, whereas if I look at this bottom one, ACD is not a face of this ordinary polyhedron, but they both map down to the same tropical polytope. And this will become an issue, as we will see soon. So that's just an overview of tropical polyhedra. We're now ready to start defining what we would want a face to be. And the definition we'll use is one of Mikhail Josrig. And it's the natural one you would pick. And it's certainly the most natural, it's certainly the most useful definition of a face if we want ordinary polyhedra and tropical polyhedra to behave nicely together. And it's as follows. If we have some tropical polyhedron P, with a minimal half-space description given by hyperplanes HA. So P is just the intersection of these, this minimal half-space description. Then a tropical face of P, we take some subset of our defining half-spaces, we take their intersection, and then finally we intersect with the polytope to make, the polyhedron to make sure that we are genuinely hitting just the boundary of this polyhedron. And so this should be the definition of a face. This is a perfectly good definition of a face for ordinary polyhedra, so hopefully it works for tropical polyhedra. So it turns out there's a few issues start to arise. The first is quite a big one, and that is that in general, tropical polyhedra do not have a unique minimal half-space description. This definition is based on the idea that we have some unique minimal half-space description, so these tropical faces always remain the same. But if you have lots of different minimal half-space descriptions, and you can flip between them, then there's never going to be like a solid definition of what a tropical face should be. If you could pick a canonical one, that might be some way to like making sure you always have the same definition of a face. But in general, I don't believe we have a canonical description. And actually, it's even worse than that. Once we're in dimension 3 and greater, we can find tropical polyhedra with infinitely many minimal half-space descriptions. And this is a theorem of Stefan and Ricardo Katz. But okay, sorry. Oh
yeah, I was just wondering, I mean, there's also the face description from just convex analysis. That's, you know, a face is a convex subset of your region, such that if any non-trivial convex combination of 2 points lands inside the face, they're both inside the face.
Yeah, so you can also do this in terms of convex holes. You do end up running into similar difficulties there, which I might be able to. I'll try and touch on the next slide in a second. But yeah, you also you get pitfalls there as well, I believe.
Cool.
Okay, so but let's ignore this issue for the moment. Let's suppose, okay, well, we pick some minimal half space description. Let's carry on with this definition of a face. Maybe things work out. But unfortunately, and this is again due to some observations from Devlin and Yu, tropical faces behave quite badly, or at least the geometry of them behaves quite badly. This is the definition of a tropical face. I'm gonna stick with here. I'll also quickly touch on the convex hole definition here. And the first main issue really is that when you take intersection of tropical half spaces and tropical convex hole, you do not get the same definition of a face. And herein lies part of the issue. So here is this example that I had from before. Again, it's an example of Devlin and Yu. And I can look at the half space whose apex is this blue dot here. And its intersection with the polytope is this big blue flap here. So this should be a tropical facet. But if we look at the vertices of this tropical face and take their convex hull, we get a much tropical convex hull. We get a much smaller subset. And so the first thing we should note is actually that the tropical convex hull is much smaller than this intersection of half space's definition. Which, okay, maybe that's not necessarily an issue. Maybe we just say, okay, well, we'll ignore that. Let's just plug on with this definition. When we start trying to intersect these faces, things get even worse. So now I can look at three tropical facets of this polytope. I have a yellow one, which kind of extends across here, a blue one, which is the same blue one I had from before, and this red one. I can take their intersection, the intersection of all three of these, and I get this kind of brown face here, who only contains two vertices, A and B. So it should be a one-dimensional face, and yet we get this two-dimensional part here. Now if we took, actually, this is a good point. If we take the convex analysis definition here and say, okay, well, actually, we'll only take convex holes, you will still get issues where, suppose I took the convex hull of A, B, D, and E, and A, B, E, and F, you'll end up with faces that look kind of like this. But if you take their intersection, they're two-dimensional faces, their intersection will still have some two-dimensional parts there. So you can still run into this issue of dimensions not matching up. So we have bad dimension counting here, and we end up with chains of faces that are longer than the dimension of the polyhedron. I mean, in this case, we've got a two-dimensional facet inside a two-dimensional face inside another two-dimensional face. So this just, the geometry here is not working. So it turns out that this actually, the more I think about it, the more this is not a bug. This is like a genuine feature of tropical polyhedra. It's a slightly irritating feature, but it really comes down to this core issue that tropical polyhedra are trying to encode multiple different Puiseux polyhedra, possibly with incompatible face structures. So just to highlight what I said a few slides ago, if we look at this picture again, I have the face ACD, the facet, in fact, ACD of this Puiseux polyhedron, but here ACD is contained within a facet, and here ACD is not a face at all. But when it gets sent in the valuation map, this tropical polyhedron has to make ACD a face, in a face, and not a face all at the same time. there's just no way it's going to be able to keep all that data in a nice way.
Can I ask you a question? In this example you're showing, are these three the only polyhedra that map to that tropical polyhedron?
No, I don't think they are the only.
So do you know them all? I mean, do you know all the combinatorial types that map to this thing?
Not off the top of my head. I imagine so.
Is there a process to find them all? I mean, maybe yeah.
Yeah, it's a good question. I don't know. In fact, I think understanding what can map down onto certain tropical polyhedra is quite difficult in general. I don't think, I'm very sure this isn't all of them. I can imagine you take this polyhedron here and coarsen A, B, F, E into one face, and that should also map down.
Just a related question. So, but then could these funny tropical faces be somehow the common denominators of the face structures of whatever can map down there, like for this AB, since
yeah, so this is in fact, I believe the correct way to try and deal with this is to try and define a notion of face that is basically the common denominator of all the things upstairs. And given the time, I'm not going to get to our results on it, unfortunately. But yeah, you can define a face structure that does this common denominator. In fact, so part of the way you would do this is these funny faces are geometrically quite are geometrically unreliable, but actually, if we can do it purely combinatorially and define faces combinatorially in terms of which vertices and rays they contain, and then do a common denominator, I think this is kind of a good starting point for, or maybe the best way you can do this, or certainly a good way of doing this. Okay, in the last 5 minutes, so as I kind of just mentioned, these the two issues I kind of highlighted was you don't have a minimal half-space description in general, and that these faces have unpredictable geometry. I won't get a chance to talk about formulating these faces purely combinatorially, but I will upload my slides, and anyone who would like to see them can do, and maybe discuss this afternoon. But in the last 5 minutes, I'd like to talk about how to overcome this first issue, that tropical polyhedra do not have a minimal or even canonical half-space description in general, and show that we can at least we can find a nice class that do have a minimal half-space description and use that to at least find a canonical half-space description for all tropical polyhedra. So the nice class of tropical polyhedra we're going to look at are called monomial tropical polyhedra, and I will define them via their vertices and rays, but they have a very nice combinatorial structure, which you actually don't need the vertices and rays for. And they're defined as follows. So we have the max tropical unit vectors, which are just the standard unit vectors, but tropical. So EI has tropical 1 in the ith entry and tropical 0 everywhere else. So it's -infinity in all entries except for in the ith entry where it's 0. And then Michael Josvik and Georg Loho defined a monomial tropical polyhedron to be the following polyhedron. It's defined via its vertices V, and its rays are all of the max tropical unit vectors. So it is the tropical Minkowski sum of the tropical polytope generated by V and the tropical cone generated by the max tropical unit vectors. But from a combinatorial point of view, it has a much cleaner description. You just look at the vertices V, and to each one you attach a copy of the positive orthant, and then you take the union of these, and so you end up with a staircase picture like so. And so these things look very staircasey. This nice combinatorics has been studied in plenty of places. It has some applications to, Mikhail and Georg's initial thing was for multi-criterion optimization, but it turns up in order theory, it turns up in commutative algebra. These things have been well studied, just under different names. The first thing that makes them very nice is that whereas most tropical polyhedra don't have a minimal half-space description, monomial tropical polyhedra always do. It's always a unique minimal half-space description, and the half-spaces are all of the same form. They are all basically complements of negative orthants. So they have this inequality description. And the way you formulate them is you look at the corners of this staircase, you place an apex there, and you take the complement of the negative orthant. You also to do this, you need to take some of the apices to infinity, but that's not a problem because these are max tropical inequalities, so minus infinity is absolutely fine. So these are always unique minimal half-space, always have a unique minimal half-space description, but this is currently only for one class. Can we extend this to all tropical polyhedra? And we can do this via looking at a generalization of monomial tropical polyhedra. I will say it's a generalization that Mikhail and Georg defined. And the idea is that if we look at a min tropical hyperplane, the positive orthant is just the 0th sector of this min tropical hyperplane. You also have d other sectors from S1 to SD, and these sectors are the points whose the SI sector is the point whose ith coordinate is smaller than all other coordinates and is negative. And so whereas before we just took the sum of each of the generators with the positive orthant, we can generalize this to take it the generators with the ith sector. And so this gives us a definition of an ith monomial tropical polyhedron. Rather than taking the positive orthant here, we just substitute it for SI. And if we take M0, then this is just the monomial tropical polyhedron we were looking at before. So here's a very, very quick example. I have a polytope here generated by V. I take its first monomial tropical polyhedron and I just sum on the first sector to each vertex. It turns out that I only need to consider these two. Everything else is already contained in there. But if I do this for all I from 0 to D, then I end up with pictures that look like this. So here is the 0th monomial tropical polyhedron. Here's the first, here's the second. And what me and Georg showed is that if you take the intersection of these, well, we just end up back with our original polyhedron. So for any polyhedron, you can take the monomial tropical polyhedron over it, intersect them all, and you arrive back at your original polyhedron. Why is this useful? Well, each of these has a unique minimal half-space description for them. And because we're intersecting all these, this gives a canonical tropical half-space description for any tropical polyhedron. It's not going to be unique in general, but it is at least a canonical choice. And so this gives us always a canonical tropical polyhedron. And if we can find some tropical phase structure that works for monomial tropical polyhedra, this means we should be able to stitch these together in a nice way to extend this to a notion of faces for general tropical polyhedra. Like I said, I have some more slides talking about how one might go about forming tropical faces, but I will save that for another time. So thank you very much.